Okay, so let's check the assumptions for our example for the deadlift Body Shop Athletics X example. So we have the first assumption that we need to be able to assume that the observations are independent. Usually this is about the way the data was collected, whether you got a random sample, etc. For this example's sake, we're going to assume that our observations are independent and there's nothing inducing a dependence among the observations. So we've got that second assumption to check, and that is that, so the first one was the observations are independent, and the second one is that the sample mean has a normal distribution. If we were to collect many, many samples, we know that that sample mean would vary from sample to sample because of sampling variability, and we need to be able to assume that the shape of that distribution is a normal distribution. So we can get that in two ways. The first way is if you know that your observations that made your sample are from a normal distribution, then the sample mean automatically has a normal distribution. The second way is to call the central limit theorem in. If your sample size is large enough, then the central limit theorem should kick in to allow us to assume that the sample mean has a normal distribution. Now, what's a big sample size? I'm going to go ahead and say that anything greater than 40 pretty much allows for you to feel very safe assuming that the central limit theorem is going to correct whatever non-normalities in the original data to allow the sample mean to have a normal distribution. Anything below 15 is a very small sample size, and you really need for that data to come from a unimodal and symmetric distribution, i.e. a normal distribution. So it really needs to be shaped like a unimodal symmetric distribution. Anything between 15 and 40 is kind of in that gray area. The further away that you start from normal, like if you have a really strong skew or extreme, outliers in your distribution, then the bigger your sample size needs to be to correct for that. Again, anything over 40, we're going to go ahead and say that you're pretty safe, assuming that the central limit theorem is going to get us that the sample mean has a normal distribution. All right, so how are we going to check what distribution the observations come from? Well, because you just have this sample. You don't have a textbook telling you assume these observations come from a normal distribution. You need to have a way to check. So the tool that you might grab for first is what you've learned in this class called a histogram. That's a way that you can graph quantitative data sets where you can see features of the shape of the distribution. However, the histogram is not the best tool since you can change the bin width, how wide those bars are, and distort the shape of the distribution. You can even hide multi-modes very easily, multiple modes very easily. So if you had a bimodal distribution, you could hide that sometimes pretty easily with changing the bin width in a histogram. In a small sample size situation, you might not even have enough observations to fill out a histogram. So we need a different tool to check the assumption. We need to have a different tool to check what the distribution of the original observations is. So we're going to introduce the QQplot. We're actually going to use a normal QQplot. And this is going to plot the normal scores against the actual observations. Now this is printed in page 46 of your printed out lecture note packet. So, and I'm just reminding you of what is in there. So the QQplot is actually going to plot what we call the normal scores. That is, it's going to give it each observation a score for where it would be, what its normal score would be if it were from a normal distribution against where the observations actually are. And so if the observations align, if where they actually are aligns with their normal scores where they should be if they were from a normal distribution, then your QQplot is going to be linear. So if they're from a normal distribution, the QQplot should look linear. If, however, we observe a shape on the QQplot, like a U shape, an upside down U shape, an S shape, or an inverted S shape, or some of the common shapes that you'll see on a QQplot, then we start to think that the observations themselves might not be from a normal distribution. All right, so I've created a QQplot here. Let's take a look at this QQplot that just came up on your screen. And let's talk about whether we think it's linear or not, what shape it has. I would say that if you squint your eyes, I know there's a little bump up here. I know you're probably seeing that it's not an exact straight line, but remember, real data is always a little bit messy. So if you squint your eyes, I don't see a really big shape being made. I see a fairly linear QQplot there. If that was my QQ plot, I would say that looks fairly linear. There's little to no evidence against normality of the data. All right, now let's take a look at another QQ plot. Oh, and let's point out that the normal scores, that R puts those normal scores on the x-axis, on the horizontal axis, and it puts the actual observations on the vertical axis. All right, so now let's take a look at another QQ plot. Again, those normal scores, which R calls the theoretical quantiles, are on the horizontal axis, and the actual observations are on the vertical axis. This one, I think we can all agree, is not linear. If you squint your eyes and kind of make everything blurry, you can see a definite U shape coming out. We would call this a U shape. That actually indicates that these observations are from a right-skewed distribution because the observations are too high at the high end of the distribution to have come from a normal, and they're also too high at the low end to have come from a normal. So it's kind of like you're smushing that left tail of a normal distribution up to the right, and you're stretching out that right tail of the normal distribution. But anyway, I just need you to know that if the observations are from a normal distribution, your QQ plot should look linear. And if it's making a shape like this one is, we're going to call that a U shape, then your observations are probably not from a normal distribution. All right, so let's practice with our example now. So we have our deadlift data, and I ran the code in R, QQ norm, and then the name of my column. I attached the data set, the deadlift Body Shop Athletics X data set, and the column that had the deadlift weights in it is called capital D, capital L. So I did QQ norm of that column, and it produced this QQ plot. All right, so now we have to see whether it looks like these observations come from a normal distribution. Well, think about the way that the Body Shop data was collected. This is weights lifted when loaded onto a bar. So if you know anything about this, the weights can only be added in increments of 5 pounds at a time. And so these observations can't be from a normal distribution, right? Because these are measured on the discrete scale, since they can only be loaded in 5-pound increments at a time. That's okay, because lots of times our quantitative data is measured in a discrete way, and we're still going to look at a QQ plot, because even though the observations can't have come from a normal distribution, they can still be, if they're discrete, because a normal distribution is a continuous distribution, they can still be from a unimodal and symmetric distribution. And this is usually treated kind of the same way as being from a normal distribution for our purposes of checking whether the sample mean has a normal distribution. All right, so let's take a look at our QQ plot. The first thing I want you to notice is this kind of stair-step pattern. You see this straight line here, this straight line here, here, and here. What that is something that's very common when you have discrete data. Those are repeated observations. The weight 155 pounds is repeated 4 times in your data set. And so we have 4 circles for the 155 pounds. And the reason that it stretches them out on the horizontal axis is because it still has to put every observation in its theoretical location if it were from a normal distribution. So it spreads it out on the x-axis, but keeps it at the same spot because the observations are identical on the y-axis. So when you see that stair-step pattern, don't worry about that. That just means you have repeated observations. So what we want to do is kind of squint and make this blurry and see whether it looks fairly linear or whether it looks like there's definitely a shape being made. Now I see at this end, you know, where that observation might be a little bit, it might be starting to kind of maybe possibly form a little bit of a U shape. But if you also just take a look like this, the bulk of your observations are fairly linear on here, right? We just got one little guy at the bottom that looks a little bit like an anomaly, and maybe this guy at the top, right? But the moral to the story is I don't see a glaring shape being made. I don't see a big U like I did in that last example that we showed you, okay? So the way that I would interpret this is, so keeping in mind these observations are definitely not from a normal distribution. We know that because it's a discrete, they were measured in a discrete way, okay? I'm going to say the QQ plot is fairly linear. And I can be thinking this. You don't need to write this when you're doing these, but this indicates the observations are from a unimodal symmetric distribution. So the QQ plot is fairly linear, and we have a sample size, a large sample size. So n equals 41. So the CLT should kick in and get us that the sample mean has a normal distribution. Okay, so that's the way you do those. You check to see if it looks like the observations came from a normal distribution. If there's an obvious skew or outliers, something that's really far from normal, and then couple that with your sample size. If it's bigger than 41, the central limit theorem should allow us to assume anyway that the sample mean of those observations would have a normal distribution.